So this whole idea of modularity maximization, we can think of it as an optimization problem, which is notoriously hard because it involves, a very a combinatorial feasible space. We start with this input, which is a simple graph, and the output is the graph with communities defined for it. And I use the kind of analogy of a maze because solving modularity maximization is a computationally challenging problem. So the first approach to modularity maximization is using heuristics. Heuristic algorithms are methods that do not solve the optimization problem, but instead try to find some tricks, some rules that following that rule gives you a reasonably good solution without optimizing it. So if you want to minimize the budget for a project, and you don't actually mathematically minimize it, but instead find this general rule that spending money on things that are not necessary is not a good idea, and you follow that rule, you have used a heuristic to attempt minimizing project cost, but you have not actually minimized project cost. So here, these algorithms, each of them is from a study, as you can see. They all work based on a heuristic rule, each of them a different rule that attempts to maximize modularity. But actually, most of them fail to maximize modularity. So what this means is that we acknowledge that there's a maze from input to the output, but we don't want to solve the whole maze because we know it's computationally challenging. So we enter the maze with a simple rule. We say that the input is in the left, the output, the desirable output is at top right. So let's enter the maze and never turn left. So this is the heuristic rule. So we enter the maze, we never turn left. We follow some algorithm whose rule is never turn left. We end up somewhere, and usually in the discipline, people call this near optimal solution or near optimal partition. And we can see how close this is to an optimal partition. So this was a topic that I've been working on for the past 2 years. So the second approach is we acknowledge the maze. We know that it can be solved. It just takes time. So we develop algorithms that actually solve this. So for example, you don't need to fully understand this mathematical formula, but for those of you who have background in optimization, you may notice that this is an integer programming problem, meaning that it's a mathematical problem. There are integer programming solvers. When you give this problem to a solver, it solves it for you. It just takes time. So this is the integer programming formulation of modularity maximization. We can just give this to Groovy, for example, which is an IP solver, and it solves it for us, meaning that it goes over many partitions, many ways of partitioning the nodes into groups, and finds the partition that has the maximum modularity. So you can see that it is slower, but we actually solve the maze. This is the second approach. Then the third approach are methods that do not use modularity, which is okay because community detection is not just about modularity. So these are essentially methods that acknowledge the input, acknowledge the output, they even acknowledge the maze, but they see that the input is outside the maze, the output is outside the maze, so let's just go around the maze, right? So these are methods. Each of these, as you can see, is a paper associated with an algorithm, and these are methods that don't use modularity. They try to find a desirable output without using modularity. Questions? Yes? Xij is a decision variable. So if you're familiar with optimization, this is the decision variable for the optimization problem. For this Xij, for this formulation, it means that I and j are not together. When Xij takes 1, it means I and j are not together. Therefore, 1 minus Xij means they are together, and therefore, when they are together, this thing will be added to the objective function. You don't need to worry about it. I just wanted to kind of show that this kind of notoriously difficult problem has a very simple integer program formulation. So we can actually solve it if the instance is not that large. Other questions? So it's a network. As you can see, it has a kind of a modular, meaning clustered structure. And depending on which modularity maximization algorithm we use on it, we get different results. So here, we have just one network. I'm trying 10 different modularity maximization algorithms. 9 of them give you suboptimal partitions, meaning that they give you a partition associated with a Q value, with a modularity value that is not maximum. And one algorithm gives you the optimal partition, meaning a partition that has maximum value of Q for that graph. So Q is modularity of a partition. Q star is maximum modularity of that graph. K is the number of communities, and AMI is a partition similarity measure. So here, I'm measuring the similarity between a suboptimal partition and an optimal partition for that network. All right. So here I'm using a graph neural network algorithm, which was developed maybe a year ago. So this is from 2022. So this is an optimization problem. I think the suitable approach, so this is an algorithm from just a year ago. They're using a graph neural network for maximizing modularity, and this is the partition they get. The modularity value associated with this partition, so the partition is shown by the colors on the notes. Modularity value is this. There are 16 communities in this partition, and the similarity between this partition and an optimal partition is 0.95. So this is 95% similar to an optimal partition. This is another algorithm, Closet-Newman-Moore algorithm from those people, and it attempts to optimize modularity. It gives you a partition with a modularity of this much and 30 communities, and it's 82% similar to an optimal partition. This is another algorithm. This is actually from MIT, the combo algorithm. I think it's relatively good, but it gives you 13 communities. The value of modularity is this, and this partition is 95% similar to an optimal partition. Another algorithm, this is just from 2 or 3 years ago, EdMot algorithm. It uses those motifs somewhere in its search for a suitable partition. It gives you a partition with 53 clusters. Value of modularity is this, and this is only 65% similar to an optimal partition. And also just visually, if you just look at the results, if you just eyeball the result, you see that it doesn't make any sense, right? Like these ones are blue, these ones are also blue, but you can see that there's no direct connection between them. Leiden algorithm is named after the city of Leiden in Netherlands, and it's from Leiden University. So it gives you a partition that is 98% similar to an optimal partition. So this is a very, very popular algorithm these days for community detection. So if you want to remember 2 names for suitable community detection algorithms, I guess one of them is Combo. This is from maybe 10 years ago. The other is Leiden, which is from 3 or 4 years ago. Then Louvain algorithm is named after the city of Louvain in Belgium. Again, it gives you a suboptimal partition. Paris algorithm, named after Paris. It gives you a partition with a modularity equal to this. This is another algorithm, Leitch-Newman, from those 2 people. Again, it's pretty good. Belief algorithm, belief propagation. And you can see that this is also suboptimal. It gives you 6 partitions. So really the result depends on which method you use. So in data science, people refer to community detection as it's the same thing. But the question is, how did you find the communities? Because depending on the algorithm you picked, you got different results, widely different results. You can use the input and get 53 communities or 6 communities, depending on which algorithm you use. And then we have, so this is the algorithm that I developed with an excellent student and a colleague from the industry. And of course, I'm a bit biased, but I think this is also a good algorithm. And it is the only algorithm that gives you the optimal partition. But it only works for small and mid-sized networks. So that's the caveat. All right, so for evaluating these heuristics, one way to compare them is we use this network. This heuristic, let's say, gives us this partition. The first heuristic says 1, 2, and 3 together, 4, 5, 6 together. The heuristic number 2 gives us this. Heuristic number 8 gives us this. And then we have this baseline, which is solving the integer programming formulation to global optimality. And solving this gives us this partition. And also the solution to this problem is not necessarily unique. We may have multiple optimal solutions. So we can use an IP solver to get all the optimal solutions to the problem. Yes? Suboptimal would be a partition whose value of Q is not maximum. So so there's a very large number of possible partitions for a simple graph, right? For each graph, there are, let's say, thousands of partitions. Each partition has a value of Q associated with it. The maximum value of Q among those would be the maximum modularity for that graph. Sometimes there are multiple partitions for one graph that have that maximum Q. So yeah. Yeah. So the thing is, for finding values of Q, we're not doing explicit enumeration. What we're doing is so-called implicit enumeration, which means finding the globally maximum value without checking all the possible cases. So that's why, for example, if we use the Bayan algorithm and it gives you an optimal partition, that is the optimal partition. Even if in 10 years from now someone comes up with a different algorithm, the value of Q should not be larger than the maximum Q that, for example, I've reported in my papers. Yes?
So we're assuming that fast modularity means fast partition.
For now, we're not making that assumption because just the focus now is on maximizing modularity. But in the next part, we're going to compare algorithms of different families based on something other than modularity so that we are fair. Yeah, for now, let's just say that the objective is maximizing modularity, because all of these methods are modularity-based algorithms. So all of them attempt to maximize modularity, they just have different success rates. Some of them maximize modularity almost never, some of them 20% of time, and some algorithms all the time. All right, so the modularity values associated to these partitions, let's say these are the values, 0.4, 0.4, 0.3, for this 1.5, and we know that this is Q star. So we know from the result of the optimization, we know that there's no way that there's a partition with a larger value of Q for this. That's why we put a star. Then we can define this simple idea of optimality percentage by dividing values of Q on Q star. So for this first heuristic method, it would be 4 divided by 5. So it's 80%. The modularity this gives is 80% of the maximum modularity. For this one, it would be 3 over 5, so it's 60%. This is one measure of performance in terms of optimality, in terms of the objective function. Another performance measure is by comparing the partition that it gives. So this is the partition we get from method 1, and this is an optimal partition. We look at the similarity between these two using AMI, adjusted mutual information. Let's say the similarity here is 90% because only one node is different between these two. But the similarity between this and this is lower. So for example, it's 70% because these two partitions are not that similar. One of them is into 3, one of them is into 2. So this would be 70%. And just by definition, for the exact method, both of these performance measures would be 100%. So as long as the exact method gives us, executes in a, kind of terminates, the algorithm terminates in a reasonable time, its performance would be 100%. Yes? We don't use modularity as a score function, but here, essentially, the optimality percentage has modularity in it. So we're not using the value of modularity because that also depends on the structure of the graph. Some graphs have a maximum modularity of 0.9. Another graph may have a maximum modularity that is 0.1, depending on the topology. That's why the value of modularity by itself is not comparable across graphs of different topologies. But this optimality percentage divides Q by Q star for that graph, and it's comparable across different graphs. So what I'm going to do is to draw a scatter plot with this on the y-axis, this performance measure on the y-axis, and this performance measure on the x-axis. If an algorithm has a good performance, everything should be at 1 and 1. Yes? The issue is the computations. So sometimes it just it needs several weeks or several months. That's it. So up to certain size and order, up to certain n and m for a graph, it is available. Just that n and m was maybe 10 and 20 a few years ago. Now with the algorithm that we've developed here, sorry? Exactly, with any NP-hard graph problem as well. Yes. So with our algorithm, we push that limit from 10 and 20 to several hundred and 3,000. Yes? Exactly. So here, in order to be kind of fair to these algorithms, I'm measuring AMI between result of one algorithm and any optimal partition for that network, and then report the maximum AMI. So that it is not about the closeness to the partition, to one optimal partition, but the closeness to the closest optimal partition. Then this means that if that maximum AMI is small, it means that the partition is dissimilar to any optimal partition of that graph. So, but this only happens 10% of time. In 90% of time, at least based on our experiments, in 90% of time, the problem has a unique solution. The optimal solution is unique. All right. So essentially in here, with the scatter plot that I'm going to show you, which is going to have this on the y-axis and this on the x-axis, AMI and global optimality percentage, I'm comparing these green heuristics using a blue baseline. The blue baseline that solves the maze against these green heuristics that attempt to solve the maze using a heuristic rule. And this is the result. So first of all, you can see that the data points are not all of them are at 1 and 1. They are all over the place. That's the first observation. What this means is that these heuristic methods would not necessarily give you the globally optimal solution. This is, again, very, very simple. I guess for anyone with optimization background, it's rather expected. But when I show this plot at conferences, some people get surprised. So here, the test cases are 80 graphs. Each data point shows one algorithm for one graph. For example, the CNN algorithm is in red, and I have 80 data points for CNN algorithm. One of them is here. This means that for this specific network, I got GOP that is 0.9 and AMI that is almost 0. So you can see that even if we are a tiny bit off from optimal, the partition could be substantially dissimilar. So the modularity doesn't have a smooth kind of surface where being 5% off is not a big deal. Even if we are 5% off, in terms of similarity of the partition, we may have a partition that is substantially dissimilar. So this was one of our two main findings a few years ago. So for this plot, there are three ways of looking at them. If we look at the y values, we see that there's variation across y values. This means that many partitions are suboptimal because, and they are substantially suboptimal. Otherwise, all of them should have been at the top. If we focus on the x values, it means that many partitions are dissimilar to an optimal partition. And the most interesting observation is if we look at the 45-degree line. So the 45-degree line shows situations where 5% suboptimality translates to 5% dissimilarity, meaning that the heuristic is acceptable because we are approximating maximum modularity. We are 5% off, so then our result is also 5% off from the suitable result. But you can see that most of these data points are above their corresponding 45-degree lines, and this tells a very concerning story. It means that even near optimal partitions are not similar to any optimal partition, which is an issue because this is not about minimizing cost of a project, that if we don't optimize it globally, it wouldn't be a big deal. In terms of optimality, we could be close to optimal in terms of modularity, but the partition could be substantially different. So this was one of our main findings. More recently, we did another study, and we looked at more graphs, so 104 graphs. These have both real networks and some synthetic networks. So LFR and ABCD are some synthetic random networks. And we did we analyzed a larger number of algorithms. And you can see that even these graph neural network algorithms, which are very popular for other purposes, they don't work that well. So this panel is for graph neural network with this many, of this size, let's say. And this one is a huge graph neural network that takes hours to train, and eventually it gives you a performance like this. So you may remember that I told you to remember names of two algorithms. Combo, this I think is a relatively good algorithm. It's from like 10 years ago. And Leiden, where is Leiden? Is again not that bad. And then again, of course, I have a conflict of interest, but you can also use the algorithm we developed here. We wanted to call it Toronto algorithm. That was the kind of obvious choice. But my industry partner was in Montreal, and with it, they thought this is not a good idea. But of course, if you develop an algorithm for this, the name Toronto is not taken. So yeah, so you can see that their performance are different. So this Paris algorithm, which kind of visually we saw that it fails, we can also see in here. EdMot algorithm, this is also from just 2-3 years ago. So you expect that the algorithms become better and better, but it's not really the case. Because Combo was from 10 years ago. It was, I guess, from a good team from MIT, but they are not that vocal about kind of marketing their algorithm. That's why actually many people are not aware of such an algorithm. I didn't know about it 3 years ago when I started working on this. Yeah. So this shows the same thing as the previous plot. So one of our main findings was that in 19 to 43% of time, these heuristics maximize modularity. So actually, most of the times, meaning more than 50%, most of the times they do not maximize modularity. But unfortunately, they are called modularity maximization algorithms. That's why thousands, if not more, tens of thousands of data scientists around the world and researchers from different fields, they think that they are maximizing modularity when they use these methods. Yeah, so it's just a bad naming. And the second observation was that these suboptimal partitions are disproportionately dissimilar to any optimal partition, meaning that if you are X% off from maximum modularity, the partition we get could be much more than X% dissimilar from an optimal partition. You had a question?
Yeah, so the ones that you said they are 90.4 to 44%, they have find optimal solutions. The rest of them, are they stuck at suboptimal or what happens?
So when did I say 90? 90 is actually pretty good.
No, you said 19 to...
Oh, 19.
Yeah,
yes,
so
the average. Yeah, I'm talking about the average heuristic algorithm. So Combo is, for example, better than the average. Leiden is better than the average.
Like, my question is like, in case they don't find the optimal solution,
yeah.
what happens?
Yes, they stuck at suboptimal.
So basically they never get out. Is it like
oh yes, these are heuristics. These are not meta-heuristics. So again, for those of you who have background in optimization, there are also algorithms like genetic algorithm, which are very popular maybe again 10, 15 years ago. These were heuristics with also some tricks to escape the local optimal, and they were popular 15 years ago. These methods that are commonly used in data science are not even meta-heuristics. That's, of course, for someone like me, it's very strange because genetic algorithm is like, we had access to it for 15 years, maybe more than 15 years, maybe 20 years. And these methods all work based on very simple heuristic rules, something analogous to the idea of never turn left. So they start with everything in its own cluster, and they do some greedy thing, merging nodes together in one cluster, and they get stuck, yes. All right, so then, but the thing is the time performance is different.
Well,
so actually this be scalable. The answer is no. Solving any NP-hard problem cannot be scalable. That's why it's called NP-hard. So in terms of time performance, there are huge differences. Here, this box plot is on logarithmic scale, so the times are logarithmic. So the differences are huge, are order of magnitude differences. So you can see that some of these algorithms have boxes that are up there, meaning that they take longer. So for those 104 graphs that I've shown you earlier, these are the solve times of the Louvain algorithm. They are almost always less than 1 second. Leiden algorithm is even faster. But for example, graph neural networks, you can see that the median time is, this is 200 seconds. These are empirical solve times on one computer, but the same computer is used for all of them. So you can see that, for example, the third Q3, the third quartile is almost 1,000 seconds, right? So the solve times are different. And of course, my algorithm, which solves it to optimality, it takes longer because it is doing more exploration. Yes?
Yeah, you mentioned that NP-hard problems cannot be scaled. I think that's only assuming that you have to find the optimal. So I think a good example of scalable, optimization for, gradient descent. I mean, it's for optimizing a neural network. Like, you're not always finding the optimal, but still we can always scale it to a very, very large neural network. So if you're not trying to always finding the optimal, so yes, it can be scaled. It can be, it can be scaled up.
Yes, but the thing is, cost of suboptimality in neural networks is very low. There is no issue with the network weights not being optimal. But here, I've just shown you that cost of suboptimality here is huge because you could be 5% off or even 1% off, and your partition is totally different. It is as if your neural network weights are totally different. In neural networks, global optimality doesn't matter. That's why we can't train them using gradient descent. Yeah. So there are situations where optimality matters, and there are situations where global optimality doesn't matter. Yeah. All right. So far our focus was just on modularity, and actually if you check community detection papers, there's a school of thought that just says modularity is terrible. The whole difficult issue is with modularity. Don't use modularity.